girls, welcome back. This is really just a bridging episode because I'm not quite decided on how things look out at what is generally called the South Pole. I introduced you to the Planisphere back in episode 12, and really it's it's a map of the stars in the sky. It's got a ground mask that shows the limits of your horizon. So, although the sky is quite big, 196 million square miles, you can't see all of it. And the parts of it that are in daylight, you also can't see. So what the ground mask does really is it helps you to narrow down how much of the sky you can see, and you can give some sense of how big the individual constellations are. Many of us, if you go and look up constellations in books, they're shown to you in isolation. They don't really give you any sense of scale of how big the constellations are. So it can be a bit daunting when you go outside and have a look at the sky and try and find your way around. When I kicked off with the glow-in-the-dark Planisphere, and the reason I did the glow-in-the-dark Planisphere is because I can pull the whole sky map off, the ground mask off, and you can see the entire sky. And this particular one goes from the North Pole all the way out to 60 degrees south, which is just inside the Antarctic Circle. So it was a good model to work with, but it's got its limitations. It's the one that, while it being luminous, it seems like a good idea for when you're out at night looking at the stars. It makes the ground mask window look very busy, and sometimes it can be quite hard to find your way around things. But worse than that is it chops off the last 30 degrees of the sky around the edge. It was a constant source of annoyance. And what I was surprised about is I got the usual objections from people about what directions the stars go. People telling me that the southern hemisphere stars go in a different direction to the southern hemisphere stars. So I did what any sensible person would do. I went out and bought one for the southern hemisphere. So what you've got here is two planispheres, one for the northern hemisphere and one for the southern hemisphere. And I did actually put these up the first time I introduced them, and kind of hoped that people would look when I said that we seem to be looking at the same sky. On first glance, they look fairly innocuous. They look like they're both showing one side of a ball. One's showing the top, the other one is showing the bottom. Look at the window on the ground mask. One of the more noticeable things is that the window for the southern hemisphere is much bigger than the window for the northern hemisphere. It claims to cover the same sized area. So unless people in the southern hemisphere have a magical sight and they can see, I worked it out about 1,200 miles, they can see 1,200 miles further than people in the northern hemisphere, there's something wrong with this. But if you look a bit closer, you'll also notice that the months on the northern hemisphere, the one on the left, the months on the northern hemisphere go clockwise around the year. The ones on the southern hemisphere go anti-clockwise. So if I take any date and stars at midnight, as the night goes along by the hour, you're going to see the northern hemisphere stars will go anti-clockwise for this, and the southern hemisphere will go clockwise. But take a closer look. The western hemisphere and the eastern hemisphere, look at where they are. On the northern hemisphere, the western horizon is on the left and the eastern horizon is on the right. Whereas on the southern planisphere, the eastern horizon is on the left and the western horizon is on the right. So anti-clockwise and clockwise is really neither here nor there. The stars are going from east to west on both models. And And the way it's been done is they seem to have flipped the map around. Okay, on the northern hemisphere you've got the North Pole or the North Celestial Pole in the middle. On the southern hemisphere you've got the perceived South Celestial Pole in the middle. Well, of course the stars are going to go in the opposite direction. You're looking in the opposite direction. But this is not some idle academic exercise. I live in the northern hemisphere. I live about 50 degrees north. So if I look south, I can see Orion in the winter months. And the thing you'll notice about Orion is it spans the equator. So I can see the top of Orion and I can see the bottom of Orion. Guess what? The stars on both are going in the same direction. They're going from east to west. So it might serve our purposes if we can get away from this clockwise, anti-clockwise thing, because clockwise and anti-clockwise are relative positions. I think we'll make life simpler for ourselves if we stick with east to west and kind of find our way from there. It might give us a better feel for what's happening up in the sky. So the glow-in-the-dark version had one redeeming feature, is it showed me the sky from the North Pole, or Polaris at the centre, all the way out to the 60-degree line. But that was really about as far as it went. So I went back to the original, this one. It's a much clearer map. It's not as bunched up, and the information, you don't get everything trying to leap out at you at once. But some of you may recall me saying when I first got onto this that I have an annoying habit of wanting to know how things work. So here you go, a busted planisphere. For one reason and one reason only, I get to see the sky map that's underneath, and I get to see the whole sky map in one go. And in the same way that I busted open the northern hemisphere one, I did the same thing for the southern hemisphere. So I've now got two sky maps, one for the northern hemisphere, one for the southern hemisphere, showing me the whole sky as it's seen from different parts of the world. I don't want to get too bogged down in whether the sky above our heads is a dome or a disc or whatever shape that it is, other than to say that there appears to be a surface of some description up there to which the stars are attached or in which the stars are suspended. It's really neither here nor there. The fact is, there is a sky up there and there are stars in the sky. What it allowed me to do is it meant I could then take the Northern Hemisphere star map and using all the stars from the Southern Hemisphere star map, I could plot the stars for that last 30 degrees around the edge. So I'd end up with a sky map that showed the whole sky in one go. And this is what it looks like. There's deliberately no labels on it. Because I wanted to keep it as simple as possible. Around the edge, you've got the months of the year that I'm not going to use at the moment. They'll be more useful later when I put the ground masks on, but I'll explain those in a little while. It's really simple enough that once you can recognise one or two constellations, you can start to find your way around the sky. Anybody in the Northern Hemisphere, the most common one you'll have heard of is probably this one. It's the Little Dipper. The Little Dipper is useful because it shows us where Polaris is, and this is Polaris right at the centre. Some of you may be familiar with the Big Dipper, which is kind of here. The Big Dipper is actually the back end of the Great Bear. And this is, I don't want to make this into an astronomy lesson, but if you just have a glance around, you might recognise the shapes of one or two of the constellations. Stars are classified based on brightness. and they start at number 0, and the numbers go up while the dimness goes down. So generally the brightest stars in the sky were category 0 or category 0, and then category 1 was a little bit dimmer, category 2 was dimmer than that, category 3, and so on. But stars, they've been categorized in stars since the middle of the 16th century, and gradually, as different scales were put together for it, they suddenly realised there was one star in the sky that was even brighter than all the bright stars in the sky, and it's this one. It's Sirius, which is in the constellation of Canis Major. So they had to, rather than change the whole scale, they had to categorise Sirius as a -1 magnitude. Now, the only reason I'm talking about magnitudes of the stars here is because standard astronomical notation is the brighter the star, the bigger the blob. So if you look, as you look around this, you'll see that some stars are bigger than others. It's because they're brighter than others. And once you start to see where the bright stars are, it makes it a little bit easier to find your way around it. As I said, if you ever glance around, there are one or two constellations on there that you can probably recognise. A constellation is simply a bunch of stars joined together to make a picture. The one that makes people in the northern hemisphere probably recognise is this one. It's Orion, and you'll have seen this in mythology books, and you've seen it in kind of junior level Welcome to the Stars type books. He stands with his head to the north and his feet to the south. You've got his two shoulders, and you can see his arm above his head, although he hasn't actually got a head. And then you've got Rigel and Saiph are the two stars that form his feet. And the thing that most people recognise is Orion's belt, which is these three stars. And underneath those three stars, hanging down below his belt, you've got three tiny little stars that represent his, well, that's not mentioned really. And the other constellation that we hear much ado about is this one up here. It's Crux. That's Crux. 4 stars. The brightest one's actually called Mimosa. That's what people in the southern hemisphere generally watch, and a lot of the legends are made up about the crossing the sky and settling in the winds and all that sort of stuff. We did a little bit about precession when we were talking about the sun and how it travels between the tropics, and then we also did when we did the moon as well. The stars precess in the same way. The constellations, I've divided them up. There are 88 constellations in the sky. The ones in green are the ones that are generally called the Northern Hemisphere constellations. You've got the blue ones, which are the zodiac signs. If you've watched anything of what I've done so far, you'll have mentioned those a couple of times. The ones that are in yellow are the Southern Hemisphere constellations. And the ones in red are also Southern Hemisphere, but they're the ones that are on the last 30 degrees of the sky. So what it means is I've got a sky map now that shows the whole sky in one go. But you'll notice that the constellations around the edge seem to be a little bit bigger than those that are towards the middle. I can only hazard a guess at why they're like that. What it's effectively giving us is an AE map of the sky. And this map sits directly above circular map of the world below. I don't want to get too bogged down in what the map of the ground looks like, because we can't quite decide that between us. But for now, what I've got now is a map that shows the sky, and I'll do the ground masks. You'll be able to see which parts of the sky you can see. If you go out and try and find a planisphere that covers the whole sky, it doesn't seem to exist. what you'll find is planispheres for different locations based on latitude, and the ground masks will show you how much of the sky you can see. Now, how much of the sky we can see is really based on our eyesight. The brighter the stars are, the further away they are that we can see them. But it actually provides a fairly small circle on the sky that you can see the stars and recognize constellations. Once I started looking at this and realised that the ground masks for the northern hemisphere and the southern hemisphere were completely different, and the available visibility seems to be grossly exaggerated for the southern hemisphere, what I did to go with this star map is I produced 3 ground masks. I've done one for 50 degrees north, I've done one for the equator, and I've done one for 35 degrees south. So I can lay any of the 3 ground masks over the sky and it will show me which constellations I can see as the sky clicks on hour by hour. If you go out and look for planispheres, as I've said, they're hard to find, especially around the equator. I managed to find one made by a manufacturer called Rob Walrecht. I found it on Amazon that it claims to be an equatorial planisphere. It's notable for a couple of reasons. One, they had really bad feedback for their delivery, and it doesn't seem to have been resolved. But the only alternative that you'll find for an equatorial planisphere is there's one made for, it seems to be aimed at, it's a Spanish manufacturer, I think. And the way they've dealt with it is they've split the planisphere into what I effectively had with 2 separate discs. And the problem with doing it that way around is you have to look one direction for looking at the stars in the north, and you have to look in the opposite direction for the stars in the south. And this is where I think we might be getting caught out in terms of how big the constellations in the sky really are. The only way we can really make a comparison is to stand on the equator and to look at the northern hemisphere constellations and then the southern hemisphere constellations and get a match for what I've got here. I've seen a few photographs from a few people around the world that have taken photographs of the constellations, and they seem to be comparable to the sizes that I've got here. So I'm kind of hoping that when people have had a chance to look at this and get a feel for what's up in the sky, they can go out and actually take a look in the sky for themselves. I've built the prototype for this and it seems to work. Because planispheres have the ground mask riveted to the sky map, it can be awkward when you want to start changing them and using them at different locations, and there seems to be an awful lot of money to be made out in the world by people selling you different ones based on different locations. As I've said, take a look on the internet, search planispheres and see just how many different manufacturers come up. I seem to have got this one to work. I did it with magnets and it works quite well. So I've got a few people testing at the moment, and once I'm satisfied that it works, what I want to do is I'm going to make it up in hard copy and also make it up as an electronic planisphere, and people are then welcome to it, and you go and you can play with it to your heart's content. You'll find your way around the sky, and more than anything I think it'll just give us a better idea of what's going on up there. One of the things that's frequently thrown into the mix on all this is people say, well, the stars in the sky don't tell us anything about the earth on which we live. And as I've said before, I'd beg to differ on that. The stars in the sky have been used to navigate around the world for centuries. They're regular. We can take timing from them. We can take locations from them. And all we need to be able to do really is find our way around up there. And that's really what I aim to do with this. But I've done it as a bridging episode, really to give people a chance to think about things and to really deal with the one enduring question. So the only constellation that gives us any problems for the Southern Hemisphere is Sigma Octantis. So I want to just get a closer look at it for a moment. If you look on the sky map, there are 3 stars, 2 down at the bottom and 1 up towards the top. I've shown them in green just to make them stand out. They're not really green. They're actually quite dim stars. And these are the 3 stars that make up the constellation Sigma Octantis. But if we spin it back a little bit, Sigma Octantis, right, the constellation is called Octans. And it was discovered in the 1700s by a French astronomer called Nicolas Lecaille. And when he discovered it, he catalogued 4 stars. What history and astronomy and everything else was made of it after that, I don't know. But what you'll notice is the stars are too far apart to make a single constellation. All the other constellations on the map work, including the ones right around the edge. But Octans doesn't work. And the reason it gets used as a counter to flat Earth is people say, well, there's a South Celestial Pole, and everybody at the South Pole can see the South Celestial Pole just like you can see Polaris. Well, I don't think they can. The furthest south anybody can go is 35 degrees, and you've seen these ground masks that I've made that work for this. I don't think people at 35 degrees south can see that far beyond the perceived South Pole. If they could, there'd be a problem, because anybody looking up and over the South Pole, the other side of the world, would be in daylight. You can only watch stars at night time. So if somebody on one side of the Earth is looking at part of Octans from one side of the world, they're not going to be able to see the other side of it. And I think Octans, and certainly as an explanation for why we live on a little ball flying through space, is largely a fiction. I can't speak to what people are seeing when they go out there and they look at it. At best, I would suggest that people can see 2 stars that are part of Octans, and at any time there's always going to be at least one of them is not visible. So all these marvellously taken, colour-corrected, high-definition, time-lapse photographs and pictures that people put up to say, here we are, this proves the South Celestial Pole, I don't think they mean anything, because they don't give us any indication of what they're looking at. As far as I'm concerned, they are blurry photographs. If somebody wants to prove that there is a South Celestial Pole, they should be able to see those 3 stars all pulled together south of the South Pole. I think the only place that you'd be able to see this constellation spinning, if indeed it existed, would be for them to be down at the Antarctic, and I don't think anybody is going there anytime soon. So there you have it, a full map of the sky. As I said a moment ago, this is not an astronomy class. There's not a test at the end of it. What you do with it is entirely up to you. I know the stars don't prove the Earth on which we live, or the shape of the Earth on which we live, but they certainly do allow us, and have allowed us for centuries, to navigate our way around. So at the beginning, this is a bridging episode. So what I'd really like to see now is people just have a look at this, see what they think, see if they can formulate some better questions for us to be asking the people who still think we live on a little ball flying through space. And after that, we can go from there. Thank you for listening.